Okay, guys, so here we go. We've started our review of last week's lectures, what I'm planning on doing. So I'm going to talk about what we talked about last week in a nutshell, and then start talking about the different sections of Module 2, where we'll start with reduction of order, and then we'll talk about characteristic equations and so on. So I'll start with writing down the outline of Module 2, so you guys know how I'm going to do this. And then, as I told you on our video conferencing session, I'll just break everything into sessions so that it won't be too heavy of a video at once. I'm planning on covering today, obviously we'll start with the review of what we did last week. Once that's done, I'll start with one reduction of order method. I'll talk about characteristic equation. We'll solve homogeneous differential equations, obviously with constant coefficients. I'll introduce you to two methods of solving non-homogeneous differential equations. The two methods are variation of parameters and undetermined coefficients. I call this the guessing method, either way. And once that's done, I'll talk about some basic non-constant coefficient, ODEs, which is the introduction of the next chapter, which will be full-blown non-constant coefficients. And we'll talk about some basic systems of differential equations, of course with constant coefficients. So let's talk about our review of what we've done last week. We started with talking about the general nth order differential equations. I showed you how that looks like with just general variable coefficients, and that was an of x dy dx to the nth derivative plus an minus, plus an minus 1x, and then lower the order of the derivative, dy dx, with an n minus 1 order, and so on, all the way to a naught of x, y equals g of x. So this was a general nth order differential equation with some initial conditions, y of x naught equals y naught, and so on. We talked about the fact that the general solution of these nth order differential equations will somehow look something like that. And there'll be an infinite family of solution curves, guys. And of course, if I have initial conditions, then I'd be interested in tracing one of these curves as my initial value problem solution, or specific solution. So either way. And we told you that you should be able to produce these solution curves on Mathematica, and also make sure that your IVP solution has a different color than the rest of them. We talked about existence uniqueness, and I did tell you that existence uniqueness not that crucial at this level, just as long as you know that a differential equation has a unique solution, and the solution exists if the coefficients of the differential equation are all differentiable. And the g of x, which is the non-homogeneous part, is also differentiable. But that's about all I want to say about that. Now, the first actual activity of last week's session was for you guys to be able to verify that a given solution is actually indeed a solution of a given differential equation by taking the appropriate derivatives. So I said if you have been given that y is equal to c1 e to the 4x plus c2 e to the minus x. And I ask you guys to verify that that is indeed the solution to a second order differential equation as such. And this is example 1 on my PowerPoint. You must be able to take the appropriate derivatives of the y given, plug them into the differential equation, and make sure that the left-hand side and right-hand side ultimately are equal to each other. And you could see this done on my PowerPoint, and I'm not going to waste time to do it. But that will be the first activity that you guys need to know how to do in Module 2. That moves us to, I'm going through the PowerPoint and reminding you guys of what took place last week. So as I'm going through it, I realized that all the slides up to the first 7, 8 slides, 9, 10 slides of my PowerPoint for Module 2, I'll talk about verifying solutions. On Module 10, we talked about differential operator notations, so you guys need to remember that. The D was the differential operator. We talked about an operator being a linear operator, and we know that derivatives are linear operators, meaning they are closed under addition and scalar multiplication. So you need to recall that. We talked about the superposition principle. The superposition principle said, and this is important, so I'm going to mention it one more time. Superposition principle basically says if the set of solutions y1, y2, y3, and so on happen to be solutions of a homogeneous linear nth order differential equation, so if these are solutions of an ODE, and that's interesting how that's weird and it changes. Sorry guys. So if y1, y2, y3, and so on are solutions of an ODE, then the superposition principle says that their linear combination will also be a solution. And so on. So there is the superposition principle in a nutshell. We then talk about linear dependence and independence. We talked about that it's not easy to find or determine linear independence or dependence by just observation or trial and error. That's why we introduced you to the Wronskian. And I'm sure you all remember that if you have and I'm just going to call this linear independence because that's what we need to have. So to show linear independence, if you recall from last week, we will find for a bunch of functions or solutions. So f1, f2, and I'm just going to do it for 3 of them, f3. So if these 3 functions are to be linearly independent, then the Wronskian must be non-zero. I mean the determinant, which is the Wronskian. So Wronskian of f1, f2, and f3, you would be a determinant of the first function, second function, third function, and their derivatives. And once you find the determinant of that thing and it's non-zero, that will tell us that f1, f2, and f3 are linearly independent. Which obviously you guys recall that means that f1, f2, and f3 are actually fundamental solutions. Let me just make that a better write-up. Fundamental solutions of the given differential equations. And once, as you recall, once you show that a bunch of functions are fundamental solutions, it would mean that they're actually forming bases that spans the solution space of the given differential equation, which means that now I can write my general solution as comfortably a linear combination of these functions. solution functions. And in order for us to be able to write that, and I need to make sure, put this in a nice box. I have to make sure linear independence exists, and I could say that ultimately. Very good. So we then talked about, guys, so obviously at this point you should be practicing finding the Wronskian for a whole bunch of functions to show that they're actually linearly independent, so you can then use them to write the fundamental solution of the differential equation and the general solution of a differential equation. Let's see, I proved to you guys the proof of the general solution theorem for a second order differential equation, meaning that if I say y1 and y2, and you guys need to learn how to do this for the exam as well, so I'll remind you of that because it's quite important. We talked about the fact that if I give you two solutions like y1 of x and y2 of x being fundamental solutions, and it's extremely important for us to know that these guys are fundamental solutions. Otherwise, you can't do what you're about to do. So we have to show that we have to mention that they're fundamental solutions, or somebody have to show that they're fundamental solutions. And if that's the case, and y1 and y2 are fundamental solutions to a differential equation, then their linear combination will also be a solution, to the given differential equation. So basically the general solution will be c1 y1 of x plus c2 y2 of x. And that you guys should be able to prove. I proved it in class last week, meaning you should be able to do this by yourself this week. Very well, and you could see the proof on my PowerPoint that's been provided for you. I'm navigating through what I've talked about last week to see if anything else I need to mention in terms of the review of what we did, and I think we are good. Very well. Well, this brings us to the end of what we talked about last week. Of course, it was in much more detail, but I just figured I'd give you guys a review and a rundown of what happened. The next video will start with actually giving you different methods that exist in this module, and the first one we're going to talk about will be called the reduction of order. So see you guys on the next video.